Hello and welcome to the Emerging Tech Horizons podcast. I'm Arun Seraphin, Executive Director of NDIA's Emerging Technologies Institute. On today's episode, I'm joined by Dr. Steve Harber of Parallax Advanced Research and the Ohio Aerospace Institute. And we're going to explore the promise of neuromorphic artificial intelligence. Dr. Harber is the Director of the AI Hardware Research Center of Excellence at Parallax Advanced Research. Building on Parallax's work in advanced microelectronics and neural networks, Dr. Harber is going to tell us about how brain-inspired computing is driving breakthroughs in national defense capabilities, including for things like drone operations, enhanced information processing, and electronic warfare. Dr. Harber, Steve, welcome to today's podcast.
Well, thank you. Appreciate it so much being part of this podcast today. Certainly I go by Steve. And to let everyone know a little bit about my background, I started out in the United States Air Force as a pilot, flew a variety of aircraft such as F-16s, B-52s, and EC-135s. I was stationed at Edwards Air Force Base doing test flights and absolutely loved it and loved serving my country as well. My academic background involves a Bachelor of Science degree in electrical engineering and robotics, along with mathematics. My master's degree is in aerospace engineering and artificial intelligence and machine learning. And then the PhD seems a little bit odd, but that's in neuroscience. And as you'll see, neuromorphics and neuroscience engineering all mixed together. So it makes a whole lot of sense. I have been working for Parallax for quite some time, and I love doing research. And this is pretty much a breakthrough in computing, both from a hardware and software perspective. And it breaks the mold from traditional Van Neumann architectures that we've had since a very long time, since the 70s and 80s for sure. It's time for a change. Thanks for having me on your program.
Oh, this is great. And so for those of us who don't know a lot about Parallax, can you tell us a little bit about the company?
Absolutely. So Parallax is a nonprofit research organization that does research in areas that involve fundamental basic research like universities, but then also applied research, which is a more mature level of discoveries, and then all the way up through production, if you will. So we go all the way through that valley of death where things can usually die or blossom. And so we dwell in that area, and we're involved in artificial intelligence quite heavily, but then also we're involved in hypersonic flight, we're involved in human factors, so a whole lot of other areas as well. And we've been around, I guess, for 4 years so far. And so we're like a high-tech startup, yet we're not for profit. We're a nonprofit research institution.
And Parallax has been a great partner to NDIA and ETI in the past, including co-hosting a great webinar on how to be a technology apostle, just over the last few months, as well as participating in our conference, for example. So, okay, let's get to the conversation now. For those of us who don't know, can you explain what is neuromorphic artificial intelligence? People are broadly familiar with artificial intelligence these days, and what's your spin on it?
Sure, absolutely. Let me start by talking about neuromorphic computing first, and then I'll bleed over to what's neuromorphic artificial intelligence. Neuromorphic computing, we model it after the brain. It's bio-inspired, unconventional computing, not how it's traditionally done today. It can be implemented in software and or hardware for that matter. Here's the big picture. The human brain performs the equivalent of 700 petaflops of computation on just 20 watts of power, about the power of an average light bulb. By contrast, a modern GPU data center burns megawatts to get a fraction of that efficiency. And so neuromorphic computing is based in work by sending spikes of information, the way neurons fire. Instead of crunching numbers sequentially, like traditional computing, this makes the system orders of magnitude more efficient than Van Neumann GPUs and CPUs. We can run neuromorphic software on those processors, and that does help with efficiency. But to get the most efficiency, you want to use a neuromorphic processor. And we'll talk more about that as the discussion goes on. To talk more into artificial intelligence, you take that kind of computing and then you go to AI with it. And it's similar to traditional AI. You first have to train the network. And then once it's trained appropriately, you then have to employ that network, lock it down, and implement it for inferencing. That can be prediction, that can be classification, things of that nature. Compared to other AI, like deep learning systems, they're certainly powerful, but they can be brittle and they're most certainly energy hungry. Neuromorphic AI brings adaptability, sparse coding, and low latency decision making. It's AI that thinks more like us.
So when you think about the hardware side of this and you get down to the processors, you're not describing a completely new kind of processing, a whole new set of different kinds of microelectronics or foundries. You're just talking about a different kind of circuit,
That's right.
right?
That's
A
right.
different kind of design, which you could use using our standard lithographic systems in semiconductor foundries. You just produce something which I would crudely call a neuromorphic chip,
Right.
which then could be used in one of these systems. Do I have that right?
You've absolutely got that totally correct. Yes. Yes, indeed.
So when you were discussing this, you were talking about it kind of modeled after systems in nature, basically the human brain.
Right.
Makes me think of all the work we've done over the years in biomimetics,
Right.
things like how lizards climb walls and how birds flap their wings. So what inspires the development of neuromorphic systems along the lines of why model AI after a brain?
Right. 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 That's an extremely good question and well thought of. We turn to the brain because it is the most energy efficient and adaptive system in existence that we're aware of. It co-locates memory and computation in the same location as opposed to off the processor. It learns on the fly and thrives in uncertain environments. Standard computing, traditional CPUs, GPUs, or think of them as calculators, number crunchers, and they tend to do a lot of operations needlessly that they don't need to do. A lot of matrix algebra, linear algebra, that just doesn't need to happen, and we don't do that in our brain. The brain is an adaptive reasoning engine. And so, if we can model that on even existing chips, and that's what we're doing best we can, we get all kind of efficiencies, more adaptability, and more resilience. And I've said publicly before that when it comes to the human machine learning and AI, neuromorphic computing makes the matchup between humans and computers not only easier, but more intuitive. That's why we model the brain.
You mentioned the power of a brain and the low power consumption of a brain. Is the brain still more powerful than the biggest supercomputer we have sitting at Los Alamos or Sandia or somewhere like that?
Actually, yes. When it comes to reasoning and decision making, with the most assured response that is going to obtain at the end of the day, a result that is of highest accuracy. Yes, the human brain's better at it, and the human brain flop equivalence is higher than the most powerful computer and system, and uses a heck of a lot less energy. So just imagine if we can model the data center like the human brain, the energy savings that, if you will, that we'll be able to obtain. So absolutely, the bio-inspired computing, if you will, the human brain is absolutely the most efficient, more so than the biggest, baddest supercomputer.
So now when I think about the applications in the military sense, in the defense sense, what in your mind are the key advantages for neuromorphic hardware over these conventional computing systems, even supercomputing systems, right? So the AI community started by using traditional CPUs, and now many, maybe largely, have moved over to graphics processing units, GPUs, right, which arguably weren't created for the purpose of AI, but have been now used by the AI sector. But you're arguing you've got advantages over both. So if I put on my Pentagon hat, what are those advantages?
Very good. Another very good question, by the way, and it's one that needs to be asked and answered. So, for example, let's talk about a neuromorphic chip. Now, there's a couple of different ways to do a neuromorphic chip. You can do it in the traditional digital sense with a neuromorphic mesh overlay. So you're still, like you said, sort of in the closer to a traditional CPU, GPU realm, if you will, other than the fact that you're moving that compute and memory over to the processor, if you will. And training on an actual neuromorphic chip, and this is rather new, if you will, but training on a neuromorphic chip is actually 2 times faster on average than training on a GPU CPU. And so training on a neuromorphic chip is a relatively new breakthrough. And we have found that you can do it with 60% fewer epochs, if you will. And so that's
What's an epic?
an epoch is one training cycle, one iteration when you do machine learning and going all the way through the loop, if you will, all through the code and training up and getting closer to a weighted equation that is more accurate, if you will. And you have to do that in iterations and reduce loss and reduce error to an acceptable level. And if you can do that in fewer epochs, you save a whole lot of power consumption and energy, if you will. And so if we can do that faster with fewer epochs on a neuromorphic processor, that's a cost savings. That's a cost savings to the defense of our country. Inference. Now let's do inference, and that is determining what is out there. So the whole idea about artificial intelligence is to be able to predict the future, if you will, to infer what that image is, what that threat is. And if you can do it 3 times faster than a GPU, which you can on a neuromorphic processor with neuromorphic software, you can do it 3 times faster. Then that means you can outwit your opponent quicker than they can. It's like having a dogfight between an F-35 and a F-4. If you're much faster, you can outmaneuver. And so that's what you get with neuromorphic computing processing, if you will. Accuracy. Okay, so we have found that when you do the right combination of spiking neural networks, it's a way of doing neuromorphic computing with spikes, as we have touched on lightly. You can mix that with a spiked version of a convolutional neural network, which is more traditional, can be heavy compute. But you can do it, we've recently discovered, in a spiking fashion. And when you do that, you can get up to 10 percentage points higher accuracy, which is huge, right? Which is huge. The example data set we used for that was a CFAR 100, because you're mixing the feature extraction excellence of a CNN with the spatial temporal excellence of an SNN, and you're getting the efficiencies of the SNN with the accuracies of the CNN and the right combination, and you improve accuracy and efficiency and you reduce power consumption. it's magnificent, and we're able to do that.
Could you take a step back and
Sure,
help us understand CNN and SNN?
absolutely. So a CNN, think of it as, let's talk about inferential statistics. Let's start there. So inferential statistics, we're all learn statistics in school. First, you have descriptive statistics on what happened in the system, and it tends to be very rather historical. And then you get to inferential statistics, which makes predictions or makes inferences of what's going to happen in the future based on historical data. Well, machine learning's a kind of that's a segue to machine learning. Well, let's go with, say, an artificial neural network. Let's go to a CNN, which is based on that, but a CNN back propagates. So it does forward propagation with the information, with the data as it trains on the data, and it randomly initially changes the weights or changes the weights of the attributes of the system to find the most efficient answer, the least amount of error. And so it does that going forward. But then we do a back propagation and we add basically first order differential equations, if you will, derivatives going backwards, looking for basically that global minima where the slope is zero, where you're getting to a minimum in error in the system, and you do that in an iterative uh, operation over and over again until you get the best accuracy, the least amount of loss. I apologize. I didn't mean to get into differential equation speak, but it was kind of unavoidable at that moment. But at any rate, that's what a CNN is. Now, I'll briefly tap on you can overtrain, and then you train on that data set and it gets real good on that, but then the system will not generalize to the real world very well. So you want to train with just the right combination of data, and accept you're going to have a little error, and you have to do that, and that's somewhat of a craft, if you will. But when you can do this with a spiking neural network, and it takes sparse data. So much like the human, right? We don't have to figure out the environment by taking 1,000 looks at the environment. Here's a perfect example. If you show me a few pictures of what a coyote is, pretty much humans know what dogs are, standard domesticated dogs, pretty much. And if you show me a few pictures of a coyote, with my mind, my brain, I can recognize coyotes pretty accurately from then on. Traditional machine learning, or CNNs, I have to show it thousands of pictures of coyotes for it to learn that with any hope of accuracy. Much more efficient than it is. But if I can do an artificial network that thinks like the human, that can do it in a spiking neural network fashion, like neurons in our mind, then I only need a small sample. I only need some sparse information, and I'll put it together. So with this artificial network, if I have orchestrated it to be like the human using spiking neural networks, which is how our neurons communicate. And that's why it's so much more efficient than a CNN.
And primitive examples of that, you're describing systems that can learn one more power efficiently, but more almost intuitively, right? More quickly in the same way a human can. And I guess this then allows you to avoid some of the early generation AI traps, like kids fooling cars by holding up t-shirts with stop signs on them,
Right, right.
right? Because the systems weren't good at context
You're right.
and weren't good at quickly learning. And you're describing systems that would be better at those kinds of
That's
things.
exactly right. It's not as brittle as traditional machine learning. That you're right. That can be fooled much easier. So a system that uses neuromorphic computing, neuromorphic technology, is more adaptive to those type of perturbations. Yes, it's more robust. Absolutely right.
When I think about military defense applications, what are the mission sets that you think most lend themselves to that style of more energy efficient and, I'm going to keep saying it, intuitive, faster learning?
So certainly, we are finding on the edge systems that operate on the edge and need lightweight. GPUs. A 4090 I know is now being superseded by, if it's a laptop, 5060, etc. Those are the, if you want a 4090 GPU, the whole system, which it comes with the cooling fan, is the size of a banana, and it's rather heavy. That's just not going to cut it on a small drone. You're gonna, and if you use the cloud, you're exposing yourself to RF going back and forth, right? That can be perceived by an opponent. And so you're on the edge, definitely out there. You want something lightweight. You still want to have that powerful computing capability, and you can get that with a neuromorphic processor, neuromorphic computing, on the edge, very fast, orders of 3 to 4 orders of magnitude less power consumed, less heat is generated, less cooling required, and very adaptive and robust. And you get that with the neuromorphic system for drones, for electronic warfare, things of that nature.
Unattended ground sensors, right?
Unattended ground sensors. So they can be very passive. And since they're neuromorphic, they're pretty much idle. So, like the human brain, if nothing's going on in the scene, I'm not going to process. Whereas, a GPU or CPU system is constantly clocked, right, at a constant rate. Well, a neuromorphic processor is not clocked. It doesn't have to be clocked. You can clock it, but you don't have to clock it. The event itself clocks the system. And so it doesn't get in the game until an event happens, and then it gets in the game. So you can be very passive, very hidden, and imperceptible. And then when something's going on, well, the event started, it's time to get in the game. It gets in the game extremely rapidly. And so it's amazing. And we found that with neuromorphic cameras as well. And that goes for space operations. We've done a lot of research recently in Martian flight. There's no GPS system around Mars. So, how are you going to navigate? How are you going to figure out your velocity? Well, we've discovered a way to do that neuromorphically, and this is funded by NASA and the Ohio Space Grant Consortium together. And we did that research and very successfully using a neuromorphic camera and neuromorphics and computing we're able to predict with extreme good accuracy what the three-dimensional velocity is of that self-contained flying drone on Mars, which is you're going to have that with these flying machines around Mars in order to not have mishaps and crashes and things of that nature. And you need lightweight durability, right? And you get that with a neuromorphic system.
How mature is the technology, on a TRL scale? Can I go to Costco and buy a laptop with a neuromorphic processor on it yet, or Best Buy, or is it something that I see at someone's lab bench and it's all sort of wired up right now and they're promising me it in 5 years?
I get you. So it's in a stage that I think we are beyond just a lab curiosity. So I think we've gotten beyond that. For example, Intel's Halo Point, which I think is at Sandia Labs, is approaching, it's working towards petaflops or petaops, if you will, 20 petaops with 15 tops per watt efficiency. And so Intel Loihi 1 and 2, and I've worked with both those processors quite a bit, is it's rather labby, and it's that part is, but it's starting to show itself as more applied. It's starting to show that. Brain chip Akita probably has, if not the first commercialized neuromorphic processor, It's among the first commercialized, and you can buy that today. And then you get support with it. Again, it's a digital-based neuromorphic processor with a neuromorphic mesh, if you will. Full-blown neuromorphics will involve something that's very analog-like, okay, like the mind. And we're working on that. In fact, I'm heavily involved in a specific um, program right now doing that. So, but yeah, so it's in that stage where it's not just a lab curiosity project anymore. But you can't go to Costco. You can't, we don't have Radio Shacks anymore. But if we did, you couldn't go to Radio Shack and buy these, right? So, but we're crossing that Rubicon River, if you will, and it's getting more commercial.
But I can buy it as a piece of research equipment today, you're saying.
That's absolutely right. Absolutely right.
Yeah.
Yes, you can.
So there's still a lot of research going on here. So who are the big players? You've mentioned some national labs. Are there industry players and academic players as well?
Sure, absolutely. So, of course, Parallax, we're heavily involved, and Intel, Neuromorphic Labs. Mike Davies is the director for this project out there. BrainChip, Akita, BrainChip's involved. IBM is involved as well. They have the True North processor out, and so there's some big players right there. Let's talk about academia for a moment. So MIT is involved. University of California and the various locations are involved. Berkeley, for example, San Diego, Rochester Institute of Technology, Penn State, University of Dayton, right here in our backyard in Dayton, Ohio, Carnegie Mellon, Zurich Technical Institute, and Manchester are heavily involved. Of course, we can't forget AFRL, DARPA, and the national labs as well are involved in this research. So, we've been bridging with various defense labs ourselves. We have partnerships at Parallax with academia and industry on this. And so we're trying to get this to the warfighter as rapidly as possible.
Do any of the systems integrators, like the Lockheed's, Boeing's, Anduril's, Palantir's, do you see efforts at that level as well?
I am starting to see some efforts with the traditional OEMs and primes. Raytheon comes to mind, and Lockheed Martin, and I believe Boeing to a degree. So yeah, they're beginning to take interest in this as well. Yes.
And how are we doing relative to the Chinese?
So it's a race. I mean, and second place is not acceptable. And we're in a tight race with China. I think from a hardware perspective, we're ahead. From a hardware perspective, I think that there's some significant areas that we are ahead on over China in neuromorphics. I know they're working on some stuff to start. They're trying to get more research towards building perform more research in the area of building something that's more equivalent to a monkey's brain, if you will. They're working on that. And from a software perspective, the race is a little bit closer. We have a slight edge, but it's closer in the software area than the hardware area. But I can tell you, we got to get the lead out, and we got to work it really hard. And I think we're doing that. I think I'm seeing that occur, and we just can't rest on our laurels and depend solely on Van Neumann architecture. We're gonna. This is somewhat of a disruptive technology, if you will, and we're gonna from a socioeconomic community in computing, we're going to have to make the shift. at some point.
So, stepping back a second, let me rewind the clock here. Tell me the history of how this area has developed. Is this a Silicon Valley VC investors going after something, or is there a longer tale to tell here? How did we get where we are now?
Certainly. Arun, there is a longer tell to tell here. So it all starts with basic research, fundamental basic research. This is a disruptive technology, and that starts there. It starts with a concept. It starts with a new kind of theory development where you find a gap in existing theory in science, if you will. It starts at the roots of science, which entails fundamental basic research. And Dr. Carver Mead at Caltech, I'm going to give him credit for the start of this. He envisioned an analog processor, if you will. And this was in, the early 80s, maybe a little bit before that, in the late 70s. And so he started that. And at the same time, the digital concept processor was a competitor. And at the end of the day, we're going to see after the long haul that the analog neuromorphic like processor is going to win out. But it was rather difficult. Basically, the science and technology wasn't ready for it. And so the digital processor went out. We've been there since, ones and zeros, if you will, and offboard memory, and then we've got Moore's law, right? That's catching up to us, and so we can always build a bigger processor, and that's what's happening now. So GPUs that you can cook your breakfast on, you can heat a room with, are getting bigger and heavier and bigger and heavier. And the data centers are showing that. And then we have, these drones that are small. They can't fly around that kind of extra weight. And so we're now finding that basic research that we spent a lot of time with, and we continue to do so down that long road, we're now getting to more of an applied research with neuromorphics and more to some new applications. And so we're seeing that disruptive technology find homes. And the homes for the military, first user likely, are going to be on the edge computations. And that's going to be stuff like electronic warfare and ISR, along with autonomy and loyal wingmen, where you have to have faster reaction time, human reflexes, if you will. Maybe you're having to interpret signals in microsecond reaction, sub-microsecond reaction. The only way to get there is going to be neuromorphically. I see healthcare, even in healthcare. Smart devices, and then of course Martian flight space, right? And so, but it all starts with basic research. We have to have that first, or we can't have these sort of breakthroughs that we're seeing and reaping the benefits of neuromorphic computing.
What do you see as the biggest challenges today as you drive towards scaling up neuromorphic systems to those defense applications or even to commercial applications? Or what are the technical challenges to overcome?
Right. So the it's a difficult kind of engineering. Not that any engineering is simple, not to imply that, but it's one that's difficult because it's not how we've been doing things traditionally. It's not digital microelectronics 101 that's taught in all EE programs across the globe, if you will. This is a different way of computing. It's a different way of thinking. It's a different way of designing the architecture of the processor. And so many universities don't have courses in neuromorphic computing, in neuromorphic architecture. So it starts there. And so we're still finding quite a bit of the research, even though applied, being done by PhDs. And some of the things that Parallax and I'm trying to do locally is I'm also a faculty member, adjunct at University of Dayton in their electrical and computer engineering department. And I teach neuromorphics and then practice it in the lab, if you will. So, and Parallax is all for that kind of coordination in the entire ecosystem. And so it's adapting a new technology, and like anything else, it's rather difficult. And so I think that makes this a challenge for folks to learn and use this technology. We're going to get there. And so I think that's it. And I think, the other one is not so much technology, but it is to a degree. And that is, economics is a big driver, or certainly a pull for technology, right? If I'm not mistaken, Bluetooth, when it was invented, if you will, there really wasn't a big consumer need for Bluetooth. It was a technology in search of a need, is what it was. Now it's used everywhere. Now there's a need and there's a market for it. And so neuromorphics, I think initially folks kind of looked, well, hey, okay, I can do it faster, I can do it with less power, but you know what? I'm getting it done with the GPU and it's taking more power. Well, now we're seeing in the military, sub-microseconds matters, in lethality. Also, data centers. We're seeing the issues there, right? Some data centers use more power than small nations do in a day. And so now we're going to see a an economic need for, why not use neuromorphic processors in the data center? Why not use spiking neural networks?
I want to get to the economic argument in a second, but back on the
Sure.
workforce. Uh, the neuromorphic systems that you're describing, then, in terms of workforce, it's not a, it's just a differently trained set of computer engineers and scientists. It's not even really a differently trained set of people working in microelectronics foundries. They're just building to different designs.
Right.
Um, is there a different set of programming languages that need to be developed, similar to what the quantum computing people are running into? That, you know, me with my great Fortran and BASIC skills will never be able to program a quantum computer. Will I be able to program a neuromorphic system? And you can tell me my Fortran's not good for anything if you want.
No, I think Fortran. I think Fortran is fantastic in mathematics. I'm experienced with Fortran, but actually, Python, right? Python is a very common language in machine learning. We can use Python to do spiker neural networks. We can use Python to do, even do hybrids with CNN and SNNs. And so we don't have to radically change the language or have a new language. It's just a little different way of thinking. There is no, absolute huge community yet, or, an absolute perfect, open up the box of neuromorphic computing tool set yet. We're heading that way. PyTorch, for example, has some things, that some tools in neuromorphics and SNNs that can be utilized. It's just the start. It's just the start. So I think that, it's there. It's just a different way of thinking. They get in a comfort zone, and folks love their GPU and CNN way of doing things. And, ResNet 50, et cetera, et cetera. You only look once, et cetera, et cetera. And so we just have all kind of folks just jumping on that. And then when neuromorphics comes in the room, you can hear a pin drop. What? You know, and so I think that, it's just this. It's just the standard when a new technology comes, of people having to learn a little bit of differences. You're right. It's not like such a revolutionary difference in how we go about it. It's a revolutionary difference in philosophy and how we compute. That's the difference. And so this is certainly doable.
Now back to the economic side, when you think about the breakthrough technologies like Bluetooth or integrated circuits, it helps to have this killer commercial app, no matter how much the government, the Department of Defense invests early on in basic research and even acts as the early adopter. So, what's the equivalent, you think, to the personal computer or the mobile phone that will drive wider spread commercial adoption of neuromorphic systems?
Sure, absolutely. I think the mobile phone market would certainly be
Hmm.
a launching pad because the processors are smaller than traditional process, even smaller than what you would find in a cell phone, and it's certainly on the edge. And you need something that has a very small power footprint for longevity and adaptability. And so I think that would be a strong market area. Um,
Is there any reason why they would generate more or less heat than a traditional
Sure, sure.
processor?
Because it's a number of operations, basically. When you're clocked and you're always doing something, unless you're turned off, and then the heavy compute that's done and the processing with Van Neumann architecture generates heat, especially at the GPU level, when you're into like a personal computer, or you're doing some machine learning on your personal computer, for example, heat generation. It's a number of operations that occur, and it's a waste. It's kind of a waste of energy because all those operations don't have to happen. We don't do that in our human brain. We don't need to be doing that in a personal computer either. Huge savings, and you can do it much faster. I think, besides the military on the edge, in space on the edge, I think we're going to see it with wearable devices in the medical community, whether they're on or inside the human. I think the data centers are going to be a huge driver. One of the so I've been an innovator for something we call it Parallax, called the living processor, and I'm working on that with some universities on doing research. And it's a processor that could be used for the edge or for the data center. And so I think that's going to be. I don't know which is going to. We know that in the military, it's going to be the edge device. It's just going to happen. In space, it's going to be the device of choice. I believe that it's going to be. I don't know what's going to happen first. Either the smartphone with a neuromorphic processor, or if it's going to be the data center. There's going to be, again, some challenges with the data center. It's a little different way of computing with LLMs, but I know we can break through that one too. So I think it's going to be on who's going to be first in the civilian market, if it's going to be cell phone or data center, but all that's going to find its way in the personal computer, and and be more, it become more the norm.
Looking forward now, if you look out in the next 5 to 10 years, what do you hope to see neuromorphic computing or neuromorphic AI in terms of its footprint in defense technology and in adoption by defense industry and the Pentagon?
So where it's going to go first in the Pentagon arena, is that your question?
Yeah, and where do you? Let's stop. Let me ask that question again.
Sure.
So, looking forward, then, project out over the next 5 to 10 years, where do you see neuromorphic computing, neuromorphic AI being first adopted by the Pentagon? And then where do you hope we are at if we have this conversation in 10 years in terms of how widespread is the adoption?
Got you. Understand completely. So let's talk about defense first. Since they're low power, that means longer endurance. And that's going to be, we're going to use it for drones. I have to see that's what's going to happen. So for those that are in the drone business, neuromorphics, um, aircraft, an F-16, for example, not a lot of real estate. And so when you're wanting to do fast compute sub-microsecond aircraft neuromorphics, and then something that we haven't talked about yet, but soldier carried systems. So, the soldier has to carry a lot of stuff already. Drones are now, enemy drones, adversarial drones are a threat. And so, I think the way to deal with that initially on pop-up threats like that is something the soldier can have at the ready that doesn't weigh much, that doesn't require a lot of space, that they could deploy within just moments to take out, say a small drone that can be lethal and take it out. Neuromorphics is the answer to that. And so, event driven speed, again, some microsecond reactions to pop up threats. It's got to be adaptive and resilient, resist to noise, deception, and attrition. So we have found in high noise environments a propensity for robustness with neuromorphics to noise. And that makes sense that it would be. And so I think that we're going to see more of that in the DoD, and then we'll see it get more widespread. Again towards, more of the, data center operation, and as well as the cloud-based systems as well. We're going to see neuromorphics go there, and so that's more. I hope all that can happen actually in 5 years. And so, 10 years from now, we'll be asking what's not neuromorphic, as opposed to what is neuromorphic, going to be what's not neuromorphic. That's what I think we're going to see happen. It's inevitable.
How much work is going on with the brain and cognitive science community that usually lives on the medical side of campus and works with NIH? Is there work going on between this neuromorphic computing AI community and those people who really do study legitimately the brain
Right.
to develop more optimal
Yeah,
systems?
absolutely. And so this is why I was very fortunate. So the Air Force sent me off to PhD school, and they very specifically said neuroscience. And again, I reminded them I was an engineer. But I once I did it, I fully understand why. It's the neuromorphic piece, and you're absolutely right. NIH is a pivotal piece in this process. For example, I work with Dr. Reshma Jha at UC and folks at Penn State who are currently have an NSF grant for a DNA compute layer. I said DNA compute layer to add to the work that we're currently doing with this living processor. And you know, and so clearly, the more we know about the human brain, the better we can make the neuromorphic processor, and we can do neuromorphic computing. And so, yes, I may be an engineer and a neuroscientist, but I need help from colleagues in this whole conglomerate of research. And so it takes not just engineers, but it takes physicists, it takes neurologists, it takes neuroscientists, different parts of the brain, the hippocampus. We have neurogenesis, and we produce new neurons in that region. Long-term memory never really goes away. And again, we build new neurons. We used to think that once you lose them, you lose them. And so the human mind is as vast as the universe, outer space, if you will. And so we need to know. There's so much about the mind we don't know, um, and the more we do know and that's going to take NIH funding, NSF funding, things of that nature, and a lot of foundational research to feed this type of thing that we're trying to feed with neuromorphic technology.
So NDIA members range from big traditional systems integrators, companies doing a lot of technology work like Raytheon and Boeing, Lockheed, you mentioned, Palantir and Anduril, to smaller companies ranging from hardware developers to software writers to manufacturing companies, and including not-for-profits like Parallax and universities. In that whole community, if people want to get more engaged with the development of this technology, where would you direct them? Are there particular journals or conferences or gatherings where you think people can see what's going on and see how they fit in?
Excellent question. So yes, there is. There are a couple of, it's fairly new, but there's a couple of different neuromorphic conferences across the nation and the globe. And one of them is hosted by Oak Ridge National Laboratory, but it travels about. And the best way to do it is to do a Google search on neuromorphic and conferences and journals. But there are a few out there. They're not as plentiful yet, but they are growing. And I highly encourage folks to go to conferences, especially with those that are neuromorphic specific, and attend those and start learning and publishing in those and presenting in those. I attend neuromorphic conferences. I also attend electronic conferences, and I bring with me research and publish in neuromorphics because the more that we can socialize the technology, even at the scientific community level, the better this is going to be accelerated here in the U.S. And so, yeah, there are conferences that are done that we can attend to do that, and they're fairly easy to locate.
That's great. Dr. Steve Harber is the director of the AI Hardware Research Center of Excellence at Parallax Advanced Research. Steve, thanks for joining us today.
Thank you so much. I appreciate you for having me. Thanks to everyone.
And with that, I want to make sure everybody visits ETI's website to sign up for our mailing list and register for our various webinars, events, and educational offerings, including our Tech 101 webinar series. If you enjoyed this podcast, please don't forget to like our episodes and subscribe to our channel to stay up to date with all of our latest content. We're available wherever you get your podcasts, including YouTube. A special thank you to Melanie Yu, Daniel Park, and Wilson Miles for producing this podcast. Thank you so much for tuning into Emerging Tech Horizons.